So let's begin then with region 1. So in region 1, we have this equation that we've just written down. And one of the nice things about region 1 is that it is a classically allowed region. So I'll just note that. So first I will make a series of statements that apply in general to any classically allowed region. And then we will get to the specifics of what applies for us in this particular example. So for any allowed region, I always am in the happy situation where the energy is greater than the potential energy, V of x. So that means that this quantity in parentheses would always be positive. So my second derivative actually equals some negative number times my function back again. And one of the best ways I can think of to remind myself that I'm always dealing with a negative number is to write it as minus the square of some other quantity. And that other quantity then is what's multiplying my wave function phi of x. And I can solve then for what this k must be. It must be the square root of this positive quantity. So in general, it'd be the square root of 2m over h bar squared times the energy minus whatever this potential V of x might be. Now that we have it down to this more simple version, let's consider the generic behaviors of a function that would satisfy an equation like this. So let's sketch that out. Now I am considering a classically allowed region. I'm only interested, in region 1 right now, so I'll just sketch what goes on this side. But the behavior I'm sketching, as you will see, will be quite general. So let's imagine my wave function phi of x has some positive value here. So phi is greater than 0 at some point. Now if I have a point where it's greater than 0, you'll notice phi would be positive, but this total quantity on the right side has to be negative. That means I have a negative second derivative, which corresponds, of course, to then downward curvature. So whatever my function is doing over here, it has to be curving downward like so. And if it curves downward, it's going to have to eventually cross the axis and enter this new regime where now, I'm sorry, my pen is getting a little shaky, into this new regime where we're now at a location where phi is less than 0. But if phi becomes less than 0, this minus sign would then imply that in fact the second derivative now in this region has to be positive. So once I cross over my axis, I'm going to be curving back upwards. I'm always curving actually towards my axis. So that's a key lesson here that's quite general. In an allowed region, those are characterized by curvature always toward the x-axis. So that's a general lesson. Okay, now let's get a little more particular now. So for us, in the example that we're actually working through, right, we can solve for our particular value of k. So k equals the square root of 2m over h bar squared times e minus v of x. But now for us, in region 1, that's what our focus is. In region 1, the value of the potential is always 0 in this region. So this v of x actually goes away. That's just 0. So we have this happy, simple result. And what's really happy about this is that this value turns out just to be a constant value for our particular example. That's going to make solving this equation surely a little bit easier. And this constant value applies only in region 1, so therefore I'm going to label this as K1, telling you that I'm focused now really on our particular case for region 1. Okay, so now I have this equation. I could even rewrite it. Phi double prime of x equals minus K1 squared times phi of x. I think we can begin to write down solutions to this equation. Now, you can probably guess from the generic behavior that we're sketching here what types of solutions we can expect. So phi of x, you might think, well, it looks like some sort of sine or cosine function. So let's check. What if it was something like cosine of k times x? And the relevant k, I'm really hinting here, if you're used to these equations, should be k1. And we can check, right? I need to take two derivatives of this function. Well, the first derivative will pull out a k1 and will turn the cosine into minus the sine function. And then when I take the next derivative, I will get another k1, so I have a net minus k1 squared, and then that sine function turns back into a cosine function. So I'm exactly back where I started from, except by taking two derivatives, I've pulled out a minus k1 squared and get my function back. So clearly this is a solution. But it's going to be very useful for us to, at this point, write down the most general possible solution to this equation so we can make sure we capture the actual behavior in our system. So just cosine isn't the whole story, right? I could multiply this by any constant, and that constant, of course, would not be touched by taking the derivative, so I would still get my function back again, and I will call this constant a1 because I'm really writing down the solution now in region 1. So that will work, but there's not just cosine, right? There's another type of function that will give the same behavior, and of course that would be the sine function, and I'm going to give that a different prefactor, which I will call b1, and then I'm going to denote this here as b1 then times the sine of k1 times x, like so, right? This then will give me an even more general type of solution, and in fact this is the most general type of solution. Because I have a second order differential equation, there would only be two free parameters in the general solution. So this is the general solution. And I've got those two parameters. Now, it turns out, though, that there can be different equivalent forms for writing down the general solution to a differential equation. So this is form 1. There's another form that very well may prove very useful to us if we think about it. Because let's look at what we're going to do with this solution. Ultimately, we know we're going to use it to build up some kind of a wave packet, right? And this wave packet has to describe two phenomena. One phenomena is where there's going to be an incoming probability packet, and then later on in the problem there's going to be a backwards moving wave packet. And so if you really think about it, there's another set of solutions which actually correspond to waves that are traveling forward or backwards, and those are complex exponentials. So another equivalent, because all general solutions have to be equivalent to each other, another equivalent form, which I might call form number 2, to solve this differential equation, would be these complex exponentials, e to the I k1x, and I will put some constant in front of that. I will call that a c1. And then, of course, I could have the backward traveling piece, so I'll call that d1 times e to the minus I k1x. Now, whichever of these two forms you use, you can use either one, and you will finally come to the correct solution to the problem. There's nothing wrong with one or the other. It will just prove, though, if you're clever about how you set up your algebra, you can keep it from getting out of control by picking whichever form proves to be most convenient for the problem that you are solving. And as we look at more problems, we'll gain that experience, and I'll make a few comments from a case-to-case basis which form, one or the other, would be better to use. So, that then sums up what we need right now to solve our equation in region 1. I would just like you to notice that what we're left with is a choice of one or two different forms, but also we are left then with two parameters that ultimately we have to determine using various boundary conditions.